All right, so we're back again. Going to start up in Chapter 6 this time. Chapter 6, we're going to talk about standard deviation as a ruler, and we're going to talk about the normal model. We're also going to talk about shifting and scaling summary statistics and what happens if we do that, how we use a standard deviation to measure spread, and we're going to talk about the normal curve as a model that we can use when we're talking about statistical data. First thing is, we want to talk about what would happen if we shift or rescale data. So let's say the class took a 40-point quiz. Results show the mean score was a 30, the median was 32, we had an IQR of 8, and a standard deviation of 6, minimum of 12, and a Q1 of 27. Now suppose you got a 35. So let's see, what would happen if I decide to weight the quiz as 50 points? Instead, what I'll do is I'll add points to everyone's score. Well, if I do that, your score is now going to be a 45. But all of my original data is going to change also. My new minimum is going to be 22. My new Q1 is 37. A new median of 42. Q3 is 45. But my IQR is still going to be 8. All the scores moved up by 10 points, so the difference is still going to be 10 points between the scores. But let's say instead, I decide to weight the quiz as worth 80 points. So I'm going to double everyone's score. So your 35 now turns into a 70. I look at all my original data. Well, it's going to double. But my IQR also doubles. I can look at that. 70 minus 54 is 16. Because not only did our scores double, those differences doubled also. So if we multiply, it looks like my measures of spread are also going to change. So let's say we want to do one more try. This time I want to make it worth 100 points for the quiz. So I double everyone's score and then add 20 points. Your score went from 35 up to a 90. And my number summary, well, my minimums turned to 44, Q1 to 74, median to 84, Q3 to 90. My IQR is 16. So my IQR did double, but I didn't add the 20 points. So multiplication affected my IQR. It also affected all of my positional data, my minimum, my quartiles, my median. That's all been affected. But IQR was not affected by the addition, even though that changed all the individual scores. In fact, we can look at it as a group, all of the data. And I didn't do the mean inside those little groupings, but if I added 10, yeah, the mean's going to change by 10. Everyone's score went up by 10, so it makes sense the mean is also going to go up by 10. If I doubled everyone's score, well, it makes sense the mean is going to be doubled also since it's the average. And of course, if I doubled and added 20, the mean would go up to 80. Okay. But we notice multiplication is what affected my measures of spread, but addition affected everything. I'm sorry, addition, I misspoke. Addition didn't affect spread, but multiplication affects everything.
What? Huh?
Now, if you're still not convinced, still can't see it, let's go ahead and look one more time. This time we're going to put some data and we're going to check it. What we're going to do is we're going to load the original in L1, then we're going to load the original data plus 5 in L2, and then we'll triple our original data for L3 instead of L3. So we're going to pull up our calculator here. And if we notice, I've already taken some time and loaded my data in my calculator, so I have it. So go ahead, pause the video, load it inside of your emulator, or if you have the TID4, load it inside of there. And then I want to validate the information I already have on my screen. You can see it back here, a mean of 6, 158. That's L1. And we know if we want to see the summary statistics, we click Stat, Calculate, one variable, L1, frequency is blank, we tell it calculate. And yeah, it tells me my mean is 6, and my sample standard deviation is 1.58. And that's what I found over here. Now if I did it for my data, where I added 5 to everything, that's calculate, one variable, but now it's L2, so I click second 2 to change that. Frequency still blank, tell it calculate. My mean's 11, it got 5 added to it. My standard deviation is still 1.58, nothing changed. But when I tripled my data, instead of L3, it tripled my mean. My mean went from 6 to 18. My sample standard deviation went to 4.74, which is, let's see, 1.58 times 3. And that's what we get. So yes, if we're just doing addition and subtraction, that affects my mean, but it didn't affect my standard deviation. But when I multiplied, that affected my standard deviation. So measures of center and position are affected by everything. Addition, multiplication, and subtraction is just another type of addition. Division is just another kind of multiplication. But measures of spread were only affected by multiplication or division, multiplying by fractions. Now, something you also have to remember, a few facts here, is that any set of numbers can have a mean and standard deviation. So I have a set of numbers here, I call them W, 5, 10, 20, 65, 80. They have a mean of 36, and they have a sample standard deviation of 34.17. But as I talked about before, we're going to use the mean and standard deviation when my set is approximately normal, doesn't have outliers. But literally, any set of numbers has a mean and sample standard deviation. So if I want to know how many standard deviations a calculation was from the mean, all we do is we find its distance from the mean and then divide by the standard deviation. Now, when we have a standardized value, this is called a z-score. And a z-score is when I take that observation, which is x, we call it x, and what I do is I take the observation, I subtract the mean, and then I divide by the standard deviation. And doing that gives me a z-score. So if I wanted to look at that number 5 out of my set W, I calculate the z-score by doing 5 minus 36, divide by 34.17, and go ahead and do that. Now I find it's negative 0.91. So what that tells me is that the observation of 5, that data point of 5, is just less than 1 standard deviation below the mean. It's a negative value, so it's less than the mean, but it's not quite a full standard deviation below the mean. Now, when we standardize data into the z-scores, we're just shifting it. We're doing this shifting and rescaling using our standard deviation. We're adding, subtracting, or we're subtracting, which is just a form of addition, and we're doing our multiplication. We're multiplying by fractions. So we're shifting our data. And when we do that, our units just become generic. Now, then this is called standardizing our data. But it's important to remember, when you do this, it doesn't change the shape of the distribution. So if your distribution was skewed to begin with, it's still going to be skewed. If it was symmetric to begin with, it's still going to be symmetric after you standardize it. But what it does do is it moves the center to 0. Your mean becomes 0, because as you remember the z-score, it was the data you want to know about, the x minus the mean was on the top. So if I subtract the mean from the mean, it's 0. But let's also change the standard deviation to 1. Because remember, if I'm dividing by the standard deviation, well, the standard deviation divided by the standard deviation is going to be 1. Now, this is going to be very useful because what it does is it lets me compare different results that are not otherwise directly comparable. It lets me compare apples to oranges by making them set to a standardized scale and then comparing them. Because I may have an apple that's very heavy. I want to say, how is this compared to other apples? And then if an orange is very large, I want to know, how is this orange compared to other oranges? And I can say now by standardizing them, if this apple, how much better is it than all other apples? And it has orange. How much better is it than all other oranges? And then I can say, well, this apple is a better apple. And in fact, it's so much better, I could say between these two fruits, it's even more, what's a good word for this? Impressive. Because it's even more standard deviations above the mean. So let's talk about that in the idea of a decathlon. So if you have to score these competitors, there's 10 events. But let's just say 2 people had perfectly tied for the first 8 events. And in the 9th event, the high jump, one of them goes 1 inch higher than the other. Then the 1500, the other one runs 5 seconds faster. Now we have to decide who's going to get the medal. What that's going to come down to is knowing whose performance, sorry about that, hit my keyboard, it's going to come down to whose performance was more impressive. Is it harder to jump an inch higher, or is it harder to run 5 seconds faster? So what I have to do is I need to standardize their results. And I want to see their z-scores relative to other high jump, relative to other running. And once I do that, I can see who did better. So we're going to try it with 3 athletes. And they have a 3-event competition. We're going to decide who gets the gold medal. Who had the most remarkable performance? If I look here at competitor A, in the 100-meter dash, they ran it in 10.1 seconds. Shot put, they threw it 66 feet. Long jump, they jumped 26 feet. Competitor B, he ran the 100-meter dash in 9.9, threw the shot put 60 feet, did this 27-foot long jump. Competitor C, 10.3 second 100-meter dash, a 63-foot throw on the shot put, and long jump, they jumped 27 foot 3 inches. And then I have the mean and the standard deviation for each event. Well, first we want to do any kind of question like this, FRQs, anything. We want to think about what we're going to do first. And like I said, to compare these athletes across different events, I need a way to compare them without the units. And specifically, I have seconds for the dash. I don't have seconds for the shot put. I need a way to get rid of those units. So I'm comparing apples to apples. So I'm comparing like performance to like performance. And the z-score does that. It removes the units. Now, we also don't want to forget, faster is better in the 100-meter dash. We want a negative z-score. We completed the 100 meters that much faster. So to account for this, what I'll do is I'll flip this sign on the z-score. So a negative for the 100-meter dash will become a positive. Then when I'm done, I've calculated all the z-scores for every event. I just add up the z-scores for each competitor, and I'll have their total z-score performance, and whoever has the highest z-score total put in the overall most impressive performance. So I'm going to use that data from the first chart, and I want to fill out this chart. Okay, now if you print the notes, you already have that other data, but if you need to, I'll leave this up, copy it down for a moment. Now pause the video. Okay, and if you're still listening, you must have already unpaused the video, so we can go back over to the screen. Now, what I'm going to do is I'm going to do competitor A, and then I want you to pause the video and try out, as I say to pause, and try each one. So competitor A did the 100-meter dash in 10.1 seconds. We know the mean for that was 10 seconds, and a standard deviation of 0.2. Now, I said I wanted to flip the z-score, so I put this negative in front of it to flip the sign. So when I do that, I find out that this person ran 0.5 standard deviations worse than the mean performance, and that's what we saw. They ran it in 10.1 seconds. The mean is to do it in 10 seconds. They were below the mean time, and 0.1 divided by 0.2 is 0.5. It's 1 standard deviation slower than the mean time. For the shot put, though, they actually performed 2 standard deviations above the mean. 66 minus 60 is 6. I divide by 3 foot for the standard deviation. They came in at 2 standard deviations above the mean. A pretty impressive performance. And we'll get into how impressive a little bit later. Now for the long jump, I have 26 foot minus the 26 foot and divide by 0.5. Now, we didn't have standard deviation written down as 0.5 for this because it was written in inches. It was written as 6 inches. So we have to remember when we do this, make sure we have the same units for our mean and our standard deviation. Since our long jump mean was measured in feet, convert our standard deviation to feet. So overall, I've now added up their z-scores, and competitor A had a 1.5 z-score total. Let's talk about competitor B. Oh, I didn't mean to click that yet. But they came in, they ran faster than the mean time. In fact, 0.5 standard deviations better than the mean time. So they get 0.5. So we're going to take a moment, try it out for their 60-foot shot put and see what you get for their z-score. Using the same formula we used for competitor A, just that using their performance of 60 feet. And what you should find is 60 foot minus 60 is 0. Divide that by whatever you want, you get 0. Now try their long jump, 27 feet. Okay? You should have found that they put in a performance that was 2 standard deviations above the mean. So I have 2 standard deviations above the mean for long jump, a 0.5 standard deviation above the mean, better performance. I'm sorry, it wasn't actually, for their 100-meter dash, it was not 0.5 above the mean, or it was not a z-score of 0.5. It was actually negative 0.5, but we made it positive so we could add them up. And the higher they get, the better they did overall. So they had 2.5 z-scores. So they're definitely better than competitor A. So we're going to take a moment, pause the video, and knock out for competitor C all the way across. All right, so it must have done it. So you should have had that they came in significantly slower than the mean time. 1.5 standard deviations slower than the mean performance. However, on shot put, they did pretty good. Came in 1 standard deviation above the mean. Definitely not bad. But here on the long jump, they did even more impressive than competitor B. They actually did 2.5 standard deviations above the mean. But that 100-meter dash time was really hurting them. 1.5 standard deviations slower than the mean performance. It's a total of 2. Now, what I've done here is I've shown my justifications for my conclusions. Now, that's what we're going to do. We're going to think, show, and tell. So the last thing we have to do is just tell. What did we find? What are we concluding? Well, B was the winner. They had a total of 2.5 standard deviations above the mean performance, which is more impressive than the other competitors. Now, I could go more in detail depending on what the question was asking me. First of all, C came in second, A came in third, with 2 standard deviations and 1.5 standard deviations above the mean, respectively, which just means C was 2 standard deviations above the mean, A was 1.5 above the mean. But C's performance on long jump was the most startling. 2.5 standard deviations longer than the mean or the average long jump. They had the most impressive single event performance. And an FRQ could ask me for all this kind of information. But since I performed that chart, I filled in that chart, I had all the information I needed. Now, we're going to move into the normal models. The normal model is very powerful because we can use it whenever we have a distribution which is unimodal and roughly symmetric. And it's called the bell shape, sometimes called the bell curve. Now, what we can write is we use capital N, parentheses, we put the population mean, comma, the standard deviation. And that's a shorthand notation for this is a normal model with a mean of mu and a standard deviation of sigma. Parameters, though, and this is important we go into this, we haven't talked about this before. Parameters are numbers that I use in a model that describe a population. Okay, so they're not just a sample. Parameters, when I'm talking about an entire population, I have data on everyone. Statistics, on the other hand, they're calculated from the data that we have in our sample of the population. And to give an idea here, let's say I want to see how well the seniors at our school were doing. Well, if I took on the SAT test, if I took all of the seniors' SAT results, I'd have a parameter. I have the numbers from the entire population. But if I took a random group of 30 seniors and used their SAT scores, I'd have a statistic. It's data from a sample. Okay. Now, we use different labels for statistics and parameters. For the mean, we use X bar if it's a statistic. Now, the calculator by default thinks you're using a statistic, so it always shows X bar for the mean. If it's for the entire population, though, we use mu. And you have to know these. For our standard deviation, if it's a statistic, we just use the letter S, usually lowercase. For a parameter, if I have data on the entire population, I use sigma. The standard normal model, we're going to always use n 0, 1. It's a curve the z-scores work off if the original data is roughly symmetric. So we can use this as long as our data is roughly symmetrical. Now, we do need our model to be nearly normal. To do this, we check our data, load it in a histogram, make sure it's nearly symmetric and unimodal. Now, that's the easiest way for us to be able to do it at this point. We've drawn histograms before, that's what we can do. The other thing you can do is use a normal probability plot and make sure that plot is linear. You look on page 119 of our textbook, we've got some examples of what it looks like, and we're going to get into this a little bit later and how we generate one of those. At this point, you may be given a normal probability plot, or I could give you a histogram, and you should be able to tell me whether or not you think it's going to fall into a normal model. Normal probability plot, it should just look like a linear plot of points, that they form a generally straight line. When our model data does fit with this, our z-score is just this. The data we care about, or z equals x, or the observation I care about, minus mu, the mean, and then divide by the standard deviation. So let's try a couple. We'll get to a couple in a second here. Next thing we have to learn about, write these down. These are very important. This is called the 68, 95, and 99.7 rule. Now, don't forget, remember the IQR gives me the middle 50% of data. But with the 68, 95, 99.7 rule. It says if I have a normal distribution, 68% of the observations fall within 1 standard deviation of the mean. 95% fall within 2 standard deviations of the mean. And finally, 99.7 fall within 3 standard deviations of the mean. Now, we can think about this for a second. 99.7%, there's a little bit left over. Yeah, 0.3 is left outside of those 3 standard deviations. Since my data is symmetrical, half that's going to be on the left, half that's going to be right. We can also draw these pictures, what we want to do. So this is what I'm talking about. In our standard normal model, we have our mean right here. 68% lands within 1 standard deviation. 95% land within 2 standard deviations. So we have 2 standard deviations below the mean, 2 standard deviations above the mean. Finally, 99.7% land within 3 standard deviations. So within is both directions. Of course, we can also fill in each column. And it's very useful to do. Once you have a normal distribution, you want to draw this curve. And you're going to hear me say a lot. Draw, shade, draw, label, shade. So in this case, I've drawn my curve. I've labeled the bottom with just the mean and minus 1 standard deviation, and the mean plus 1 standard deviation, plus 2 plus 3, minus 2 minus 3. We said 68% lands within 1 standard deviation. Well, half of it's on the left, half of it's on the right. So I have 34% in each of those areas. So if I ask how much landed in what percent or what proportion of the population would be represented from 1 standard deviation below the mean all the way to the mean, it would be 34% of the population. That's what I expect. Now, going on from there, what I would do is I'd use my 95% rule. Let's see how that would work. So we have our 95. And we've already accounted for 68%. So I subtract that 68. That means I have 27% left over. I divide in half because it has to be symmetrical, or I have 13.5% in each side. And that's exactly what I had. That's also how I found my next column, which is 2.35% on each side. And don't forget, this is percentages. If these were decimals, I'd have to move the decimal place twice to the left. Finally, I've got that little bit left over in the tails. We said it's 99.7% is all of this combined. So I've got 0.3% cut in half. I have 0.15 in each tail. Now, if the data doesn't fall exactly on 1, 2, or 3 standard deviations from mean, we use table Z. And I have a separate video that goes into a lot of detail using our Z-score tables to find this. We can also use the TI-84 to find some of these data values for what proportion land within a certain value. I'm going to be using the TI-84 for the rest of this video. The other video I post on this goes into the tables, and we have examples using the table of the book. You need to be proficient with both. But let's say we have this, we're going to describe fuel efficiency of cars. So for the next few examples, we're going to talk about cars. They have a mean of 24 miles per gallon, and a standard deviation of 6. So I can fill out my chart right here. I've got 24 miles per gallon as my mean, minus 6 miles per gallon, minus another 6, minus another 6. And working upwards, I added 6, added 6, added 6. So if someone was to ask me, or if I could describe this by saying, I expect 68% of cars to get between 18 to 30 miles per gallon. I expect 95% of cars to get between 12 to 36 miles per gallon. Finally, I expect 99.7% of cars to get between 6 and 42 miles per gallon. Now, I haven't thought about 100% of cars. Technically, the normal curve continues forever in each direction. Now, usually when we're talking about things, we have approximately normal distribution. We have roughly symmetrical, because obviously I don't have cars getting negative miles per gallon. I don't have cars that make gasoline. But it's kind of trivial to talk about 100% cars. They get somewhere between 0 miles per gallon up. I don't know what the max would be. We normally are only going to describe these 3 standard deviations in each direction. If I have to describe a normal distribution, that's what I'm going to describe. Now let's say someone asks me what percent of cars get less than 15 miles per gallon. Like I said, we want to draw, label, and shade. So first thing is I draw and I label my mean. Then I'm going to mark the 15 miles per gallon relative to that mean. It should be below the mean. Lastly, I would shade in that area of the graph because that's what I want to know about. In our case, I said we're going to use a calculator. So let me hop over to our calculator because 18 miles or 15 miles per gallon does not land directly on one of our standard deviations. So I want to convert that to a z-score. When I do that, 15 minus 24 divided by 6 at negative 1.5. Now is when I pop over my calculator. Whoa. So now I'm going to use my calculator, and what we're going to do is we're dealing with a distribution here. So in our calculator, we look this little blue, this is DISTR, our distributions. So it's second vars, and I want normal CDF. We'll never use normal PDF, but normal CDF we'll use. If I go into it, it says, what's your lower? How far down do you want to go on the normal distribution? If we remember, it looked like we're going to go, no, let's get back onto there. We're going to go all the way down. We're going as far down as it can go. So, negative 1e99, that's pretty far. However, if you simply put negative 99999 for the z-score, that's quite a few z-scores down. Our upper, we said was negative 1.5, so negative 1.5. Our mean, we convert to z-score, so our mean is 0. Our standard deviation is 1, and we paste this. So calculator is telling me that 0.06 or 6.68% of cars get less than 15 miles per gallon. Oh, I forgot these. I'm using a z-score table in the book. That's what we'd find out. So we expect about 6.7% of cars get less than 50 miles per gallon. Or I could also say, if I picked a car at random, there's about a 6.7% chance I'm going to pick that car and it'll get less than 15 miles per gallon, because the proportion of cars and the chance of getting a car are going to be kind of the same thing there. So let's say I want to know what percent of cars get between 20 and 30 miles per gallon. Well, again, 20 doesn't land right on one of those standard deviations, so I can't use my 68, 95, 99.7 rule. So I want to draw, label, and shade. So I've drawn my curve and I marked my mean. Now I want to mark my 20 and 30 on here. Then I'm going to shade in between them, because that's the area I want. And that picture where I've shaded between 20 to 30, that's going to help me make sure I put the right information in my calculator. That tells me for my lower, it's going to be whatever the z-score is for 20. My upper, it's the upper part that I've shaded through, whatever my z-score is for 30. If I calculate that, my z-score for 20 is negative 0.67. My z-score for 30 is 1. So I go normal CDF, second vars, normal CDF. Lower we says negative 0.67. Upper is 1. I leave it 0 and 1 because it's a standard normal distribution. I paste that in. So 58.99% of all cars get between 20 and 30 miles per gallon. Now, of course, I can still mark my z-scores on my graph. That's what I'm looking for. I want the area. How many z's? What proportion of cars will have a z-score between negative 0.67 and 1? We found that out around 59%, and that would be acceptable on this. Get between 20 to 30 miles per gallon. Let's go ahead and try another one. What percent of all cars get more than 40? So again, I draw, I label, and then I shade above 40. Now I want to, so like we've done before, now I convert to z-score. So take a moment, pause the video, convert this to a z-score, and think about what you're going to put in the calculator now. Okay, so if you convert to z-scores, so we've gotten 2.67. So we have our z-scores. Now the only thing is, now we have a lower, we don't have an upper. I'm just looking for z's above 2.67. So let's see, if I go second vars, normal CDF, the first time we had a lower of negative 9999999 because we wanted to go far enough below the mean. Well, this time our lower is 2.67. So now we want to get all the standard deviations above, just plenty of them. So again, I just put in 5, 6, 9s. Mean is 0, standard deviation is 1. Paste this in. 0.0038. So 0.38% of cars. I expect 0.38% of cars get more than 40 miles per gallon. That's not very many cars. It's pretty rare that a car gets more than 40 miles per gallon. No, maybe some of these. You're not carrying much in there. Maybe a small toolbox on the back, a sack lunch. That's about it. We can also ask it a different way, though. There's other things we can do with this normal curve. I can say, well, what's the fuel efficiency like for the worst 20% of cars on the road? We don't know their miles. We want to find it. But I know they're the lower 20% of cars. So I don't know what the z-score is, but I know that part of the curve is 0.2 or 20%. Well, we have another command. I can use a z-chart and look for that lower 0.2. Where are they at? Where's that left-hand side of the graph is 0.2. Or I can use inverse norm. Let's see how that works with the calculator. So I go second vars, because I'm still in distribution. And here's my inverse norm. It asks me for area. Now the calculator always works from left to right. The area I want is on the left and it's 0.2. Has a mean of 0, standard deviation of 1, because it's a z-score. And I get a z-score of negative 0.8416. However, that's a z-score. This is in miles per gallon. So I need to actually convert that negative 0.8416 into miles per gallon. Well, normally z-score, the z equals x minus mean over the standard deviation. So I just plug in what I know into the formula. I know the z is negative 0.8416, x is what I'm looking for, minus the mean, which we said is 24, and a standard deviation of 6. So I can literally just do, I got to convert these, multiply both sides by 6, negative 0.8416 times 6. And that's going to be negative 5. And on the other side of the equation, it's to be x minus 24. So I'll just add 24 to both sides. I have 18.95. That would be my x. So I know that 20%, that 20% of cars get no more than, let's say that number again, 18.95 miles per gallon. So worst 20% of cars have fuel efficiency of less than 18.95 miles per gallon. No, this is where we're talking about our Hummers and our H2s and H3s. They're not getting the best mileage. So what gas mileage represents the third quartile? We're tying this back to the other stuff we've talked about. And for quartiles, we say quartiles represent 25% of the data. So my third quartile is 75% of the data. So take a moment, think about this one for a moment, and how would you attack this problem? We'll come back. Now pause the video, think about it for a second. Okay. So like I said, we know it's at 75% cutoff. So I'm going to inverse norm my 0.75. I'm going to get 0.674. So my z-score is 0.674 that I'm looking for. But I want that as gas mileage, so I have to put that back in our formula and solve for it. And when I do, it's 28.04 miles per gallon. So the third quartile is going to be about 28.04 miles per gallon. Now, since that's the third quartile, that's Q3, that also represents the upper 25th percentile. Remember, this is symmetrical, and we have to keep that in mind about where these quartiles are. If I ask for the first quartile, I'm asking for the bottom 25%. Or I could be asking for 75% of cars get better than what mileage? And that'll be my area to the right will be 0.75. So make sure you read the question, draw these sketches, sketch them out, and label them. It's definitely what's going to help you get to the right answer. In fact, I'd say what's the fuel efficiency of the most efficient 5% of all cars? So pause the video, get the sketch on here, go through and try this problem, and then come back to the video and let's see what we do together. All right, so if the video is playing, that means you must have finished the problem or at least gotten as far as you could and need a little bit of help. Well, first thing is one of the most efficient 5% of all cars. So it's at the top of my graph of 0.05. I'm going to inverse norm this, just as we did before. Second, vars, inverse norm. Now this time I want the top 0.05. Now, if I do 0.05, remember the calculator always adds from the left going up. So it's going to tell me that negative 1.64. But I know I want the top, so let's see what I get. Second vars, inverse norm. Well, the top 5%, the area on the left must be 0.95 because it all has to add up to 100%. So if I do this, well, I get positive 1.64. So remember, our graph is symmetrical. So my z-score at the top 5%, that'll be the same as my z-score for the bottom 5%, except reverse the sign. So doing that, I have my z-score of 1.64. Then I just need to convert that over to miles per gallon by putting it back in our formula of 1.64, that's my z-score, has to equal x minus the mean divided by standard deviation, or 33.84. So there's my gas mileage. The most fuel efficient 5% of cars on the road are going to have the lowest mileage is going to be about 33.8 miles per gallon. So they're going to be better than that. Now we have this interesting thing. I'm sorry, we'll go back up. So we'd expect them to have better than 33.8 or in excess of 33.8 miles per gallon. Now we have some other questions we have to talk about. What kind of gas mileage would I consider unusual? Why would I consider it unusual? There's a lot of answers to this kind of a question. It's going to depend how you define unusual. There's a couple rules of thumb that are out there for this. You have to identify which one you're using unless you're being told which one to use. One of the most common ones we use is if you're more than 2 standard deviations from the mean on the normal model, that's going to be unusual. So in this case, it would be any gas mileage below 12 miles per gallon or anything above 36 miles per gallon would be unusual. We've also talked about our IQR and outliers, though. That those were 1.5 standard deviations above Q3. They would be outliers, or 1.5 standard deviations below Q1. So I have to think about this for a second. We said our graph is symmetrical. So on the left is 50% of my data. On the right is 50% of my data. So the question is, what z-score would be Q1? Well, let's see. Q1 is a 25th percentile. So I can do second vars, inverse norm, 0.25. Or negative 0.67. But if I want to go further than that, I have to go 1.5 standard deviations below that. My standard deviation is equal to 1. So I need to go 1.5 standard deviation, 1.5 times my IQR. My IQR is 50% of the data. So I'd have to go a bit further. We'd have to use our standard deviation, multiply by our standard deviation by 1.5 and move it further down further to the left. It's all in outliers. But when we're using the normal, it's just much easier to use this 2 standard deviations rule. That if I'm moving 2 standard deviations below the mean or more than 2 standard deviations above the mean, that's what we're going to consider unusual. Now, if you're given one where it says 3 standard deviations is unusual, we'd use a normal model. We'd say less than 6 or more than 42. Normally on these, we're going to use a 2, but sometimes it's going to say use 3. Normally we're going to use 2, though. You get to decide which of those to use. I would definitely not try to use the 1.5 times the IQR, below Q1 or above Q3. And if you really want to go into that one, we can get together and I might make a separate video for that, for where you would end up. Because it's one that you would generally have to calculate, because it's not a number you're going to memorize and keep with you. So I might make that a separate video for this. Maybe I'll make it an extra credit assignment. We'll see. So let's say I want to know what percent of cars get under 20 miles per gallon. So take a moment, try this one on your own. When you come back, just going to work through the solution. I'm not going to go back and forth to the calculator. I'm going to show the numbers I got. All right, so you're back. Draw a label shade. What percent get less than 20? My z-score is negative 0.67. When I put that in, normal CDF, negative 99. I just put 2 nines this time. 99 standard deviations below the mean is pretty far down. I get 0.2514. So 25.1% of cars get less than 20 miles per gallon. That's not that many. That's actually a pretty good amount of cars. 1 out of 4. So that's actually, a good amount of cars get less than 20 miles per gallon. Such an ecology group says they want to get the national gas mileage at no more than 10% of cars running 20 miles per gallon. Now, if the standard deviation isn't going to change, what would my new average fuel efficiency have to be? Well, let's think about this for a second. they want to get no more than 10% of all cars be less than 20. So I know right now they want that figure to work out to 20 miles per gallon is only 10% of cars. Well, I have to inverse norm that at negative 1.28. So doing that means 20, that needs to be negative 1.28. That's the z-score I'm curious about. Now, I've said the standard deviation isn't going to change. So let's plug in what we know and what isn't going to change into our formula. Z has to equal, so negative 1.28 has to equal 20 miles per gallon minus the mean divided by 6. That means the new mean gas mileage needs to be 27.68 miles per gallon. That's pretty significant increase, actually. That's almost a half a standard deviation. It's actually more than half a standard deviation increase. So some car manufacturers might say, we can't handle that. We cannot make that happen. Instead, they're going to have to work on something else. They'd have to change the standard deviation. There's only so much they can change. So what's their new standard deviation going to have to be? Again, they want their mean to stay 26 miles per gallon. That's all they can make happen. They still want that 20 miles per gallon to be no more than 10% of cars. We inverse norm it, we still get negative 1.28 because it's 10%. It's going to be negative 1.28. We plug in what we know, and we solve for our standard deviation. Or negative 1.28 sigma has to equal negative 6. Our sigma needs to be 4.69. So what I'm doing is I have to shrink the standard deviation. I have to get my cars to be much more consistent in their mileage so the average difference from the mean goes down. This may be something they can achieve. They might be able to make cars more consistently so they don't have as many cars getting really low mileage, but at the same time they're going to have less cars getting really high mileage too. They've kept those cars. Maybe they just dumped the Hummers, and doing that brought that mean gas mileage up quite a bit. Now that could do that. You can think about that. What would some advantages be of this program? What could some potential disadvantages be? We saw a picture before about a lot of times these low gas mileage vehicles, people like them because they're larger vehicles. They can haul more things in them. You know, that smaller deviation to the curve is going to change a few things. People might not get as many trucks though. So before you get into that, people might not get as many trucks. Might be more smart cars on the road. Who knows? Maybe that'd be safer. Maybe it's not. You know. But smaller standard deviation, let's see what it does to the curve. The first thing is we have our standard curve. If I've shrunk the standard deviation, what I'm doing is we can picture it almost like it's reached out and it's pulled the data more towards the center. So that peak is taller in the middle is what it might look like. It's pulling everything in towards the center. That standard deviation is shrinking. It's like almost harder to get away from the mean now. So it would just mean in this case we have more consistent gas mileage. Well, maybe they can make that happen. Okay. And this is what it might look like. Where before, this 8 miles per gallon was 3 standard deviations from the mean. Now that 8 is going to be many more standard deviations below the mean. You see our new third standard deviation below is only going to be 11.93. It's not going to make it down to 8. That would almost be 4 standard deviations below the mean. If you remember from our tails before, this tail only has 0.15% in it. There's not a lot of room in there. There's not many cars in that position anymore. So, maybe this could work. I don't know. Now, again, the other thing is, though, we'd also have less cars on the higher end because the standard distribution is symmetrical. So, it's important to think about that. I also know that the 10% of cars are going to be higher than 10 miles because inverse number 0.9. Well, instead of being negative 1.28, now it becomes positive 1.28 because the other side of the curve. I go and solve it. I found it's 32 miles per gallon. So, rest of this chapter was just read chapter 6. Send me emails if you have a question about it. Ask it in class. Try the suggested problems. The answer key for that has been posted. And also go in and make sure you do the assignment that's been posted for this chapter. Don't just do the suggested. Don't forget, actually do the homework. I look forward to seeing you soon. Good luck with this. If you have questions, make sure you ask. We're going to be using this information for the rest of the year.